Good morning, mathematicians. How we doing? How are we doing? I should make more shorts. They're easy to make. Good morning, mathematicians. I should cut up more of my existing videos into shorts as well. No, that sounds like it takes too much energy. What am I saying? Bad idea. Hello, Edit Smith. Hello, Lola. Well, I wasn't planning on visiting Reddit first, but the title of this post caught my eye. We now acquired enough background in algebraic number theory. You want to go deeper into the study of cyclotomic fields, since they seem to be special cases. True. Dirichlet characters, analytic methods. How much complex analysis is required? Not that much. I mean, some basic complex analysis. Yeah, exactly. Top answer is correct. I'm pretty sure. Yeah. Okay, let's get back to Langlands nonsense. So, if you want a representation of the Weil group, well, that's just the same as picking your favorite Galois extension, or favorite finite extension of the p-adic numbers, and writing down a representation of that group. And then, at least for us, for a Langlands parameter for GLN, I mean, should be a homomorphism into GLN-C. So this is a Langlands parameter for GLN-QP, or GLN-F, I should say. Where the part, so actually I should tell you, here's the slightly more complicated thing than just restricting phi. So what I called the infinitesimal parameter before, so that's just the part, good morning tenacity, that's just the part on here, is where you specifically plug this matrix in. Actually, I should call this omega w to the half, omega w to the minus 1/2. And right, so this should be, so it's not quite just restricting to the first factor. You have to plug this specific matrix into the second factor. Sometimes call this d sub w, depends on w, as a shorthand. Yeah. And and also the condition has to be, so the other factor, if we restrict phi, and now I do mean just ordinary restriction, so it's a homomorphism of SL2C. Remember that this is entirely determined by picking just a nilpotent element in the Lie algebra of GLN, which is just to say some n by n matrix, and we want the one other condition, that if you conjugate by this for all w, you just get the result of multiplying by Q. It's in the Q eigenspace. So, yeah. And so we saw an example of this. We computed a space yesterday where we saw we could identify the points with different we could write down a space where the points correspond to all of the Langlands parameters with infinitesimal parameter given by lambda. And of course, the space we found has infinitely many points, but actually, if we just care about those Langlands parameters up to isomorphism, there's really just sort of, we could break the space into two pieces. So this represents like one isomorphism class, and this represents another. Better turn off my group chat. So, where do we go from here? There's a lot of places we could go from here. Maybe one thing to mention, it would be nice to have, like, one could imagine we write down a more complicated space. How do we find a way to break this space up into disjoint pieces that correspond to the different isomorphism classes of Langlands parameters? Well, it turns out that here's what we do. So basically, two infinitesimal parameters, or really two Langlands parameters, will be said to be equivalent if there's an element G that conjugates so that the images are conjugate. So, some G in GLNC. Right? But now, if we want to look at those infinitesimal parameters that satisfy not just up to equivalence, but like, let's say bang on the nose, we fix a representative for an infinitesimal parameter. And I want to look at all of those where, bang on the nose, like these are equal as functions. Well, then I'm not allowed to, so I want to conjugate. I want to be able to conjugate my Langlands parameters, but I don't want to rearrange, I don't want to change this thing at all. So essentially what I want is I only want to restrict my attention to those G, which, if I were to conjugate this, it leaves it fixed. So in other words, I want to look at all of those G and G that leave lambda fixed. Actually, there is something more complicated going on here. This isn't the right definition. In the case where lambda is not trivial on this group, but I'm going to sweep this under the rug for now. Maybe we can talk about it later if you really want. Yeah, there is an important intermediary step one needs to take there, but maybe I should just tell you. Basically, you just before you do this, or actually, I think for the group, this part is okay. Yeah, it's in the construction of the variety. So, anyways, the point is, so if we want to just look at equivalent Langlands parameters with a given infinitesimal parameter, we should only look at H which conjugates only conjugations by h that fix lambda. And so in turn, this h lambda gives us a action on, I'll call this the Q, this will be the Q eigenspace of lambda, of conjugation by lambda. So yeah, sorry. So the point is, right, basically two Langlands parameters are equivalent if and only if their images are conjugate, which is, this is actually something I don't quite understand. That seems to be a weaker condition than saying like the functions are literally conjugate like this. That seems to be a weaker condition, but maybe for GLN it just works out to them being just conjugate like this. I don't know. I'm a little confused by that. I'm sure with a moment's thought I could absolve myself of this confusion, but I'll just keep sitting with it for years instead of doing that. So the point is that this then, because this is just the adjoint map, basically, more or less, we have this group, you know, when we're talking about conjugating the images, we can view the group as acting on GLN by conjugation. So this descends to a map of the Lie algebra, and in particular, it will preserve the Q eigenspace, right? So I'll write it, add lambda, say we have some x in the Q eigenspace, and, well, add lambda, add gx. What is this really? It's lambda of g x g inverse lambda inverse, but since lambda fixes g, I mean, basically that means we can switch the order of lambda and g here. But now this is just conjugating x by lambda, so that is so it just becomes q times gx g inverse, and so add gx is still in the Q eigenspace. And now, so this is cooked up in such a way that now 2 points, say x and y, are in the same h lambda orbit if and only if their Langlands parameters, the corresponding Langlands parameters, say phi x and phi y, are equivalent. Isn't this diagonalization? No, it is not diagonalization. The only similarity here is we're just conjugating stuff. But nice way of saying hello. Great. So this is great. This gives us a sort of nice way to, at least if you know, at least if you have in mind the infinitesimal parameter part of your Langlands parameter. So basically, if you fix some sort of Galois representation of an extension of your p-adic field, and you say, I want to look at all the Langlands parameters corresponding to this, now we basically have a very nice way to characterize all of those, which basically just in some sense boils down to linear algebra, right? It's just like, what do? You first you write down the those matrices, which I mean, you have to know what your lambda is first. There is also one intermediate step, I should say, is first you look at those elements. So here's the thing I missed that becomes significant if it's not trivial on the inertia subgroup. You have to look at you have to look at what am I saying here? The points that are fixed by the image of everything in the inertia subgroup, and then after you do that, then you look at the add lambda, the Q eigenspace of this. So the points parameterize are parameterized by this, which, by the way, because this is just an eigenspace, it's a vector space. So this will be isomorphic to C to the M for some copy of M. So as a variety, it's very simple. But now you basically look at this collection of this group acting on here by conjugation. You basically do some linear algebra to look at the orbits that this breaks up into. For example, I'll answer your question in a second, New Wave Infantry. I just want to finish this thought here. So, for example, we've seen this case for the infinitesimal parameter given by this. We saw basically the space that we constructed was all of these matrices, and we deduced that the way to break it up was to the, again, I'm sort of abusively just writing the x-coordinate, was into these two pieces. So can we see that in terms of the group? Well, again, remember in this case, because lambda was trivial on the inertia subgroup, it basically just reduced to looking at conjugation by lambda at Frobenius. And when you plug Frobenius in here, omega takes Frobenius and returns Q. So our group, H lambda, should be everything in GLN such that G commutes with Q1 half 0 Q minus 1 half. And so, I mean, basically, just like we did last time, I'll let you do it, yourself. Just write X, Y, Z, W, and plug it in, and ask yourself which entries can be non-zero, and you end up finding that H lambda is just the torus. So it's all invertible diagonal matrices. So just diagonal matrices with both entries non-zero. And of course, why are these the only orbits? So how does conjugation by this matrix act on this matrix? Well, it's just S x t inverse. And so clearly, if x is 0, this can only ever send it to 0. So certainly the 0 matrix is indeed its own orbit. And then if x is any, s and t are allowed to be any non-zero complex numbers. So if x is not 0, we can divide by x. So you could say take t to be x, and s to any other non-zero complex number. And then we see that this pair of s and t would send x to y. And so we have this, the orbit is just all of the non-zero stuff, which exactly lined up with our other way of doing this computation. So basically we have, there's a little more to it than, yeah, no, that's it. So basically Langlands parameters for GLN, these are in bijection, and actually this holds more generally, but there's some extra complications. Langlands parameters for GLN are in bijection with orbits in V lambda. Okay, sorry, New Wave Infantry. Sorry that took so long to get to your question, but I want to finish those thoughts. What is the simplest way to explain the idea between quasi-coherent sheaves, and why are they nice? Well, that kind of depends on what your idea of easy is. I mean, if I say, well, they're like vector bundles, but they form an abelian category. I mean, to me, that's like, oh, yes, that is a good explanation, right? But for some people, that's like, that's a bunch more nonsense words that doesn't clear anything up for me. So I don't know. I don't know how you feel about that. But for me, that's a perfectly reasonable explanation. Yeah, so very roughly, well, as I understand it, vector bundles fail to be an abelian category. But given say if we're over like a sufficiently nice like complex manifold or something, then a vector bundle, if you have a vector bundle on E, then if you take the sheaf of sections of your vector bundle, this will be quasi-coherent. And yeah. And so I think in complex analytic world, you go back and you can get an equivalence. In algebraic geometry world, yeah, there's something that goes wrong here, I think. But the more sensible definition to take is quasi-coherent. And I guess in this case it ends up being richer. Also, I mean, so the category of quasi-coherent sheaves on spec R is equivalent to the category of R modules. So basically a quasi-coherent sheaf, it's something that is like locally an R module. So in particular, though, a quasi-coherent sheaf, if you have a space X and the structure sheaf, a quasi-coherent sheaf is an OX module. So there's a very stupid answer to your question of what sheaf isn't quasi-coherent is just literally write down any sheaf and neglect to define the structure of an OX module on it. And trivially you're done. Yeah. So that's a very stupid answer, but it's a valid one. Yeah. I don't know what orbital subspaces are. Yeah. Also, this is, despite my channel name, this isn't K-theory. So, well, there is some K-theory that factors into this, but not really. So, yeah. So I don't think orbital subspaces come into play, but then again, I don't know. because I'm not familiar with the term. The Luna slice theorem in this context. I don't even know what that is. Luna slice theorem. Luna's étale slice theorem. Who's Luna? Describes the local behavior of an action of a reductive algebraic group on an algebraic variety. Oh, well, that definitely seems applicable. Is an analog in algebraic geometry of the theorem that a compact Lie group, well, definitely the groups I have in general aren't like compact or proper or whatever. So on a smooth manifold has a slice at each point. In otherwise, a subvariety that looks like that. Interesting. Yeah, I don't know. Yeah, quasi-coherent sheaves are just R modules, basically. Well, okay. No, it's more complicated than that. But yeah, locally, they're things that look like R modules. Just doing some research your professor does about the orthogonal direct sum of orbital subspaces, constructing n-fold tensor spaces. Interesting. Let me see. Orbital subspaces. A subspace of a vector space performed by repeatedly applying a linear transformation to a single vector. Interesting. Yeah. Yeah. Not so clear if this applies here. But there's also, I was talking the other day, actually someone who doesn't work in this area asked an interesting question about, there's something else I haven't talked about. Well, I have talked about at some point, but related to Langlands parameters. Actually, so maybe let me just talk about it in the context of Langlands parameters. They were asking about essentially taking like tensor products of Langlands parameters. And then geometrically, this should give you a map between so if we have two infinitesimal parameters, we should basically get a map between the products of these two varieties and the like tensor product of these two infinitesimal parameters. And then so there's like, I don't know, there's an interesting question of like what does this mean geometrically? Of course, this takes you from Langlands parameters of GLN, of pairs of Langlands parameters for GLN and GLM, and takes you to a Langlands parameter for GLNM. So what should this mean? Actually, so here's the other thing. Maybe I won't have time to start talking about it today, or maybe I will. I don't know. But what I haven't talked about yet in this whole story is the representation theory side of things. So I talked about there's this bijection here between Langlands parameters and some orbits and some varieties. So that's great because it gives us some like geometric parameterization for the space. But a while ago I mentioned that there should also be a bijection. Well, it's more complicated. So for GLN, there should be a bijection between the set of irreducible representations of GLN and Langlands parameters. Sometimes we write phi g for the set of Langlands parameters. I should mention though that for other groups this becomes a little more complicated. In fact, the map from representations from representations to Langlands parameters just becomes finite to 1. And then, so we need to enhance this, and so we get what's called an enhanced Langlands parameter. So it's not just a Langlands parameter, but, well, one way to view it, and surprise, surprise, I was talking all this stuff about different kinds of local systems and whatnot. One way to view it is, in order to promote this back to a bijection again, is the thing that goes in the second component is a local system on the orbit associated. Okay, this isn't the most common way to phrase it, maybe. It is in my world. Sometimes this is phrased a bit differently. The asymmetry he proved in his paper has that same form. Interesting. Of like a map between tensor products? Yeah, so, well, speaking of, so the question is, if we have this operation on Langlands parameters, then what should be the corresponding operation on the representation theory side of things? So there is a way to go from basically this to direct sums, and I'll probably talk about this. At some point. So there is a way to go between direct sums, and in this case, the direct sum map corresponds to this. So you're going from GLM to GLN plus M. And how does this work? This has something to do with what's called parabolic induction, which we'll get into soon enough because it's a really important idea. Basically, GLN plus M, you look at these two groups, you look at the diagonal, you look at the subgroup of diagonal n by n matrices and m by m matrices viewed as a subgroup, and you simply take the corresponding, you take like two representations, pi and sigma, on here, you form, and the way to glue them together is you take what's called maybe the external tensor product, and then you look at the parabolic induction of that, and that becomes a representation here. And so that's sort of the representation theoretic thing that corresponds to parabolic induction here. But then the question now would be, well, what operation can we perform that corresponds to taking tensor products? Yeah. And there is some sort of, there's this like Rankin-Selberg stuff that I don't understand at all, that has to do with like tensor products of L functions and products of automorphic forms and stuff. And so presumably there could be something here. He's using coset spaces and n-fold tensor products using representations. Interesting. Oh yeah, I was going to go back to this Luna slice theorem. Quotients of reductive groups. Algebraic analog. Reductive algebraic group. X is an affine variety. Okay, great. So we're in this setting. Acted on by G. Such that X is smooth at X and the isotropy group is reductive, which is also the case here. Ooh, then there exists a morphism. Ah, we've got something into the tangent bundle. Um, Interesting. Hmm. Yeah, what are applications of this? If G is reductive, acts linearly on a vector space, and there's a closed orbit. Well, these orbits I have, there's only one closed one ever, and it's always the zero matrix, the origin. Then there's a all points of the same orbit type. Interesting. Anywho, it's above your head. Well, that's okay. It's always there'll always be math above your head, and my head, and everyone's head, and that's a good thing. Because if there wasn't, then you'd be done with math, and that would be the real tragedy. But if you're enjoying the ride, then that's what matters most. That's what matters most. Yeah. Okay. I think that'll do it for today. Who knows what nonsense I will talk about tomorrow? Probably I'll go back to talking about the representation theory of GLN, which I've already done extensively, but I don't know. Unless people have questions. I feel like I've really driven the vibe of office hours in the opposite direction of what I want to do. Since I came back, I've just been coming out of the gate with like very particular specialized nonsense specialized to my field in particular. And I feel like there's been a lot less random questions in chat because of that, but it's fine. I'm